Today's quick tip is about generating a procedural rope. As always, with Houdini, there are millions of ways that you can use to generate a rope, but I want to go the code route. I want to create a Vex wrangle that generates a rope for me. And once I have this, I want to sweep it to turn it into actual geometry, because first I want to create strands. And later on, I intend to simulate it using grains. So a very simple setup, but nevertheless quite useful sometimes. So follow me and let's directly dive in and generate a Geo node. Lay it down and call it rope. Dive inside and get rid of the file sub. Instead, let's lay down a wrangle. But today we don't want to use a point wrangle, because we want to create points, so we don't have any points yet, and the point wrangle is running over points. And as we don't have points, let's create an attribute wrangle instead, and let's switch this run over behavior to detail only once. And that means that the node just cooks once. No efforts are made to parallelize this node, so it's just executing whatever it finds here once. But to execute, it needs an input. So let's put down a null and connect it here, just to make it execute. Well, now we can press Alt-E over the code field here to open the code editor. Let's think about what to do to generate a rope. Well, a rope is normally composed of individual strands, and these strands are basically spirals. And what is a spiral? It's a circle stretched out in one direction. So maybe it's a good idea to start with a procedural circle. And if you remember your math class, 9th grade, something, with trigonometry you can generate a circle easily. And for this you need the cosine and the sine, because these two trigonometric functions give you the coordinates of the unit circle. The very first thing we want to do is to create a variable holding the resolution of our circle. I call it point count, so it's an integer, p and t, c and t, that's point count. And I want to create a parameter to specify this variable. So channel, but in this case, be careful, channel I, because it's an integer, otherwise it throws a warning. And let's call it point count, like so. Now that you have this, press apply, and now you can press this button here in the parameters, and it will create this field. Let's start with 100 points for now. So we intend to create 100 points. So let's write a loop that just counts to 100, or 99, because it starts at 0. So let's put down a for loop. For integer is a counting variable. It's called I, and it is initialized with 0. And it should count up until I is smaller, or as long as I is smaller than point count, p and t, c and t. And it should be incremented by 1. Now brackets, like so, and everything that is between these brackets will be executed 100 times. And first we want to create a new vector variable holding the position of the point to be created. And this is a vector, and I use set function because I want to create the vector dynamically. And this vector has 3 components, 0, 0, 0 for now. So think about it. The z coordinate should be 0 because we intend to create a 2D circle. So for the x coordinate, we use the cosine function of the angle. And for the y coordinate, we use the sine of the angle. And now we can vary this angle to create points around the circumference of this circle. And how can we do this? Well, we need a step angle. So we need the angle between 2 points, and then we can just multiply this angle by I, and thus we create coordinates around the circle. So let's first calculate this step. Let's create a new variable called step, float step. And this variable holds the entire circle divided by the point count. And what is the entire circle? Well, angles are measured in radians here in Vex, so the entire circle is 360 degrees, and that means it is 2 times pi radians. And this is divided by point count. And this gives just the angle between 2 successive points. So now we can go in and say we want to calculates a cosine of I times step and the sine of I times step. Great. Press apply. No error so far. Let's check. So what's left is to generate the points. Use add point. This function needs a geometry stream to work on, which is 0 in our case, and then we want to pass on the position variable, like so. Apply, and you see we generated a procedural circle with 100 points. And this control here can be used to specify exactly how many points to generate. 100. Like so. Now let's add the ability to scale the circle, or to set its radius. So introduce a new channel. This is float, called rad internally, and then it will be set by a channel called radius, like so. Generate the channel, first apply, then generate the channel, and there we have the radius, say 1 for now. And now we can just multiply the cosine and the sine functions by this radius, because these functions are assuming a radius of 1. So if we now just multiply by rad, same with the sine, we introduced the possibility to change the radius. Cool. But the circle, we need a spiral, and the spiral should stretch out in z. So we have to change the z coordinate. And we do this pretty much the same way that we generate the points around the circle by using a step variable. But for this to work, we first need the length of the entire thing. So let's create a length, float length. And let's create a channel for this length. Like so. Apply, and oh, we have an error here because I accidentally typed 0 instead of equals. Apply. Create this channel and set it to 2 for now. And now we can introduce a line break here. We can create a second step variable, length step this time. And this will be the length of the entire thing divided by point count. But be careful here, this is a typical garden fence problem. We don't have to divide by point count, but by point count minus 1. Because there is 1 less gaps between the points than actual points. Like so. Now we have a step for the length. We can create something for the z coordinate. And that is just I times, no, small I, times length step. Like so. Press apply. And there is our spiral. This spiral looks not very spirally, and that is because it just turns around the circle once, so it has only 360 degrees of turn over the entire length. So let's introduce something to set this. Let's create another float called revolutions, with another channel called revolutions. Like so. Apply, create this, and set revolutions to 5. And to make this wind 5 times around the circle, just use revolutions to multiply 2 pi. If you do that, you increment the entire length of the circle, basically. Like so. Now we have 5 revolutions, but only 100 points. Let's create more points, 300, say. And you see now we have 5 revolutions. That is nice. Now we can set the point count. We can define the radius. And we can say how long the entire thing is. And we can say how many revolutions we want to have. Say 4. Like so. Great, that's a spiral. But it's not a rope yet. The difference between a spiral and a rope is that a rope is composed of many spirals. So we want to create a second loop that generates more than one of these spirals, and then we want to offset them with a certain angle to move them around the circle. So let's encapsulate this loop here in a second loop. So another for loop. This time we use j as a counting variable, so int j is 0. And this loop should count until j, or as long as j is smaller than strand count, a variable not yet introduced, j++, and then brackets, open brackets. And now I indent all of this just to make readability better, like so, and close the brackets of the outer loop. And now we want to introduce strand count. So int is, or int strand count is channel integer, chi, and the channel is called strand count, like so. Now up strand count to 5. And we still just have one strand, but if you middle click on our attribute wrangle, you see that we have 1,500 points instead of 300. That happens to be 5 times 300, because we are actually creating 5 strands. It's just that they are all in the exactly same place. So we have to offset them around the circle. And how can we do that? Let's introduce another step variable, this time called strand step. So float strand step will be, again, 2π, which is the entire circle, divided by strand count. So that is the angle between 2 successive strands. And now we can use this angle to offset the individual strands. We can just add this angle to the angle we already have here. So I times step plus, and this time j, because this is a strand loop, times strand step. Let me make this window a little bigger, and then just copy this and put it here inside of the sine function too. Apply, and now we have 5 strands that are offset. If we make the radius smaller, this already looks like a rope. Perfect. So what's left is to connect these points to form primitives, because we need lines to be able to generate geometry from it. So think about it for a second. We want to generate 5 primitives, 1 primitive per strand. So the creation of the primitives has to go up here in the first loop. So int n' for new prim is add prim, geometry stream is 0, and the type of the primitive should be polyline, like so. Now it creates 5 primitives, and the very, very last thing to do is to add the points to the primitives. And that can be done using the add vertex function. But for this to work, we need a variable storing the point. So let's introduce a new integer variable called new point, npnt, here, that stores the created point. And after that, we can add vertex and just say geometry is 0. The primitive to add the vertices to is n', and the point that should be added is npnt, like so. If we apply now, the points are gone, and we are left with primitives. And here is our very basic procedural rope. So let's close this window, and to turn it into geometry, let's use the polywire node. Just append it here, and it happily generates geometry from this. So maybe let's decrease the radius to say 0.25, no, 0.25. Like so, and then we want more divisions, say 9, and here we have our rope. Maybe we make the radius of the entire rope a little smaller. Yeah, something like this. And now let's increase the lengths to say 3, and the revolutions to 6, and here is our rope. Now for simulating this. We don't want to simulate this heavy geometry. Instead, we just want to simulate one strand in the middle of the rope and then transfer the simulation to this geometry. So to do this, let's generate a line that is exactly the length of this thing here. So put down a line sub, like so, and it should be in the Z direction, and the length should be the same as the rope. So just copy parameter and paste the parameter here to length, paste relative references. Now we have a line that is exactly the same length. Now let's resample this to generate more points from it. Like so. Turn on point display, and here we have our points. Now let's set the initial variables or the initial attributes that are necessary for a grain simulation. For this I use a wrangle, this time just a point wrangle. Set initials, like so. First thing I want to set is the mass of everything to 1. And then I want a new float variable called rad, which references a channel called radius. And I want to transfer whatever I put in this channel to the attribute called p-scale, which is the size of the individual points. Like so. Now to check if this is working, first generate this radius here, and then quickly put down a sphere, a unit sphere, and a copy to points, and copy the spheres onto the points. And now we set the radius a little bigger, and we want to set the radius just as high as necessary to make the spheres barely touch, like so, 0.5. Great. This is just for checking purposes, so get rid of the sphere and the copy to the points. That is our rope. Now, before we go into simulating this, we want to fixate the first and the last points, because the rope should be pinned there. And it's easy to do that with grains, just setting the mass to 0 for these 2 points. But to do that, we first have to select them. The easiest way to select these 2 points is using a group expression, because they happen to have just one neighbor, because they are the endpoints. So if you go to the group expression, call this ends, then you can write neighbor count of geometry 0 and the current point ptnum should be smaller than 2. And of course, this group should group points. And if you do that, you see by this yellow indication that these 2 points get selected, because only these 2 points have a neighbor count that is smaller than 2. Cool. And now I can put down another wrangle, point wrangle, that only executes for the ends group. And here I set the mass to 0, like so. Now, I prepared my rope for the simulation, but for a grain simulation, I cannot use one long primitive with a lot of points. Instead, I need 2 point pairs that are connected by one single primitive. Fortunately, there is a sub for this called convert line. Convert line. And what this does is, it turns this one primitive into small primitives. So if you turn on primitive numbers, you see here this point wrangle has just one large primitive, number 0. And as soon as you put the convert line there, you have a lot of primitives connecting 2 points. And a very convenient thing is that it automatically computes the rest length which is needed for the simulation too. So now we have a line prepped for the simulation. Let's put down a DOP network. DOP network connected here. And let's create a grain simulation inside. For this we need a pop solver and a pop object. Connect the object to the solver to the output. Then we need a source to put geometry into the pop object, so a pop source. Connect it here. We need a gravity force. And that is a basic particle setup. So at the moment we don't see anything. That is due to the settings of the pop source. Emission type is set to scatter onto surfaces, but what we want is all geometry. And we don't want to use this parameter value here, but we want to use the first context geometry. As soon as we set this here, we see our geometry brought into DOPS. There it is. And now we want to go to birth and limit the birth of this to the very first frame. So $F is 1. It should only create the geometry in the very first frame. And if we now press play, everything falls down. We can disable guide here to see this better. Everything but the very first and the last particle, because these two have a mass of 0, and with a mass of 0, they won't move. So that's a particle system, but to make this interconnected, to make these constraints work, let's put down a grains node, pop grains, and just connect it here. Now this pop grain node is in charge of simulating this instead of the pop solver. Nevertheless, everything just falls down, and that is because the explicit constraints are weighted with 0, so they are not being calculated at the moment. Set this to 1, and now we have a rope. This rope is quite springy at the moment, and that is due to the constraint iterations. We have 20 constraint iterations at the moment, which is quite low. First, go to Solver and check Use OpenCL to make computation faster, and then up the constraint iterations to 100. And this will increase the stiffness, as you can see here. Cool. Now we have a wire that is falling down dynamically. Let's go up one level. Now follow the last thing to make the setup complete. We want to deform this geometry here by this dynamically simulated wire. And to do that, we can lay down a wire deform. A wire deform is built exactly for this purpose. But it needs some prerequisites to work. First, we need a wire capture to tell the wire deform how to deform the geometry, and then we need, again, just one primitive, because the wire deform works better if it has one large primitive instead of all these small primitives. That is easy to do, just throw down a wrangle, and this wrangle will be fed with the line that we had before the convert line, so this one primitive thing. This one here will be fed and say match point pause. And the second input will be connected to the results of the .NET. And now let's just type add p, which is a position, should be add op input 1, which is a second port, underscore p, which is a position. So by doing this, we now have one primitive that moves exactly like the result from the .NET because we just transfer the point positions. Great. Let's use this for the wire deform. Now the wire deform. First we have to capture the points. And this wire capture has two inputs, the geometry to capture and the wires to capture with. So the geometry to capture is our rope. And the wires to capture with is this large primitive, this undeformed primitive that we had in front of the .NET, like so. So turn off this. First we have to go to the wire capture. Let's turn on visualize weighting, and you see that we have a orange color. That is not good. Everything should be red, because red means everything is captured. So let's go to the capture tab. First let's press initialize from primitives. That means it just puts primitive 0 here because we only have one primitive to capture with. And now let's just increase the fall off until everything turns red. That means now the entire rope is captured, which is not very problematic in this situation because you only have one rope. If you happen to have more ropes, this might be a little fiddly. Okay, now we can do the wire deform. We have 3 ports here. The geometry to deform, which is this wire captured geometry, then the rest wires, and the rest wire is just this undeformed wire, and then the deforming wire. And the deforming wire happens to be this here, the one wire we create from the output of the .NET. And if we now switch the wire deform on, you see that it now deforms the geometry to the wire. We can go to the wire capture and turn weighting off to get rid of this coloring, and now you have a dynamically simulated high polygon rope that uses a low polygon or just single strand simulation to do the simulation actually. So great. This is how you create a procedural rope that can be simulated. And the best thing is that you now can go in and can add more strands, for example, because everything is procedural, and you can increase or decrease the revolutions, and you can just specify how your rope should look while it is already simulated. So that was today's quick tip. Thanks a lot for listening. I hope you learned something, and see you next time.
Let me say a very big thank you to all our patrons, especially Mohammed Al-Abri, Mikhail Ivanov, Rob Bryant Jr., Rafik Anadol, Chris Hebert, Nick, John Kunz, and Joseph Howard. Thank you so much.